Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of rational functions for a college algebra course, which might also include trigonometry. You should have already watched my videos on review of rational functions, including their definitions and the definitions of the asymptotes. There is also a set of videos on identifying vertical and horizontal asymptotes, as well as talking about the domains and also slant asymptotes. So to continue into that topic, we'll talk about the multiplicity of a vertical asymptote. And to be very honest with you, it's not actually a multiplicity of a vertical asymptote, it's the multiplicity of a zero for the denominator, but that's okay. We'll still call it multiplicity of a vertical asymptote. So let's suppose that we're handed a rational function, r of x. And sorry, my screen does this every once in a while. It's a very slow refresh on my end. Let r of x be a rational function where the numerator is some polynomial and denominator is some polynomial. That's by definition of a rational function. Also, let's suppose that this rational function is simplified. That is, you've prefactored it and canceled any like factors. So at that point, as mentioned in a previous video, you now know the domain of the function. Also, you know where you have vertical asymptotes and where you have holes in the graph. Remember, holes in your graph happen when a factor is in the denominator, but then after simplification, that factor gets canceled out of the denominator. And then because of that, you still have a domain issue where that factor in the denominator would have been zero. However, it's not a vertical asymptote. It's a hole in the graph. Anyhow, if you still have factors in that denominator, like x minus c raised to the k power, so that could be like x minus 2 to the 10th or something like that. If that's a factor of the denominator and it's the largest such factor involving that x minus c, in other words, you can't factor out any more powers of x minus c, then we would say that x equals c is a vertical asymptote of odd multiplicity if the power is odd, or even multiplicity if that power is even. Now, a definition by itself doesn't really help you out, so let me go ahead and illustrate this very quickly. Let me zoom in before I do that. So here's just a made up rational function that, let's suppose, was prefactored for us. Now, this is not ready for us to actually start talking about vertical asymptotes because there is a little bit of shared factors going on between the numerator and denominator. You should cancel those out. When you cancel those out, you need to mention to the world that x cannot be a -1. That is, your graph should have a hole at -1. Because if you just erase these and hand this to somebody else, they'll think that -1 could have been plugged in, and that is actually not true. The original rational function could not have taken -1 as an input. It would have caused not only division by 0, but the numerator would have been 0 at the same time, and that's called indeterminate. You don't need to know that right now. It's a calculus idea, but it is true. Anyhow, so what this definition is telling us is if you take a look at that simplified rational function and you take a look at all of the factors in the denominator, the factors in the denominator are x, x minus 2, and x plus 2. And the powers on those factors, 3, 1, and 1. So if you build a little table here, you could talk about what the corresponding 0 is. For example, for x, the corresponding thing that would turn that into 0 is 0. For x minus 2, the corresponding number that would turn that expression into 0 is 2. And x plus 2, the corresponding value of x that would turn that into 0 would be -2. And then you talk about the multiplicities. Now, normally, if these were X intercepts, I would be very exact with their multiplicities. I would say the multiplicity of X is 1, the multiplicity of, the multiplicity of 0, the 0 at 0, is 1, the multiplicity of the 0 at 2 would be 3, and the multiplicity at -2 would be 1 as well. But that's only necessary if you're talking X intercepts. When you're talking about vertical asymptotes, which is what these will lead to, all you need to note is, are they odd or are they even? And these are all odd multiplicity because the powers are all odd. So that's what I'm saying. If the powers are odd, then it's odd multiplicity. If I had, for example, changed this to where that was an x plus 2 squared rather than just an x plus 2, then this vertical asymptote at x equals -2 would be an even multiplicity vertical asymptote by that definition. Now, that definition might not be a rigorous definition or a stated definition in an algebra textbook, but that's a definition then I am creating. And one last thing before we jump into actually graphing rational functions is, what do you do with that multiplicity? And you might already know this, but if you don't, it's a good kind of idea to treat. And if you do know what I'm about to say, it's a good review. So if you have as a vertical asymptote at x equals c, and it's odd multiplicity, and we saw that in a previous example that I just created, that you could have odd multiplicities on your vertical asymptotes or even multiplicities, then the rational function has the opposite behavior on either side of that vertical asymptote as x approaches c. And I'll show you what I mean in a moment. If the vertical asymptote is of even multiplicity, then the rational function has a mirrored behavior on either side of the vertical asymptote as x approaches c. Let me give you just a simple one-shot example. So here in black are some the x and y axes. And then in red, I just have created some fictitious vertical asymptotes. And in green, I have a horizontal asymptote. Again, this is all just for a fictitious, made up rational function. And in blue, just to keep the color scheme going wacky, I will go ahead and draw a rational function. Remember, the horizontal asymptote is the tendency for your rational function as x goes to positive or negative infinity. So if you have a horizontal asymptote, your function, your rational function, will approach that as x goes to negative or positive infinity. Let's suppose it does something like this. Something like that in between there, maybe. And then finally something like this. Okay, so let's just suppose that this is our graph of our rational function. Well, because the behavior for this first vertical asymptote, the behavior on the left-hand side is that it's going to positive infinity, your function is. And on the right-hand side, your function's diving down to negative infinity. That tells us that the multiplicity of that 0 at x equals, let's pretend that's x equals -7. I know that's a multiplicity odd vertical asymptote because the behavior on either side is opposite. So that's what we mean by opposite behavior. And mirrored behavior is just like this next vertical asymptote. It's mirrored behavior because on one side, your function is rising to positive infinity. And on the other side, it's also rising to positive infinity. So therefore, that mirrored behavior tells us that that vertical asymptote, which let's pretend is at x equals -2, is an even multiplicityed vertical asymptote, because it has the shared mirrored behavior. So anyhow, that's just to give you a heads up of how you could use the multiplicity of a vertical asymptote, honestly, to help you graph. And that's exactly how I end up using vertical asymptote multiplicity. And that's what I highly recommend you do as well. Now, without further ado, let's go ahead and hop into some graphs of rational functions. So here we have a function that you likely have seen several times if you've been watching this lecture series on rational functions. So we're going to go ahead and graph this bad boy. The first thing you need to do, just go back to old school algebra. Always think about mathematics in terms of how you learned things. You learned arithmetic first. So if there's any simple arithmetic you can perform here, you would do that. And then after learning arithmetic, you learned algebra. And part of that algebra was factoring. The early parts of that algebra was factoring. So that's what we're going to do here is factor. So there we go. We've done our factoring, got that out of the way. And then you look through all of that factoring and you look for any common factors. And when you cancel any common factors, you should definitely make a note what happened. So you should say that x cannot equal a -4, because if you don't do that, you're going to forget that x couldn't be a -4, and it'll just disappear just like this out of your memory, and you will forget to put an open hole at -4, which is a problem. It would be wrong. So let's see, what else did we learn in algebra? Oh yeah, I know what we learned. We learned all about X and Y intercepts. So notice I'm just kind of climbing my way through algebra, factoring, and then we learned a graph at some point. And when you learn a graph, you really talk about intercepts quite a bit. Now, the interesting thing about rational functions is that finding the Y-intercept is less important than finding the X-intercepts. So I will just go ahead and put here X-intercepts. Note, and this was kind of a surprise to my calculus students, some of them, when they heard me say this, you should know that an X-intercept occurs when Y is 0. That's not the part that shocked them. So these just mean, actually I'll use a different color here. You're just going to let Y, which is our f of x, going to let that be 0. Now, just as an aside, if you let 0 equal our function, well, our function is a fraction. It's a fractional expression is what I would call it, or a fractional function. And if you take a look at any fraction and consider the fact that you want a fraction to become 0, the only way a fraction can ever become 0, and this is where my calculus students went, I never thought of it that way. The only way a fraction will ever become 0 is if its numerator is 0. I mean, that's the only way a fraction becomes 0, is if the top, which is the numerator, becomes 0. So all I would want to do here is really look at that highlighted stuff and say, when does that become 0? You should also mention the multiplicity of those zeros. So X-intercepts occur at 3. And by the way, that's multiplicity 2. Notice with X-intercepts, I don't say even or odd. I actually state the actual multiplicity of that. And for the second expression, or the second factor, the 0 is at 2/3 and it's multiplicity 1. And that just tells us what the graph looks like as it goes through or bounces off of those X-intercepts. Notice that if you watch my video series in the order that I've presented it, then you've already reviewed polynomial functions and how to graph them. And part of that was talking about the zeros and their multiplicities for polynomial functions. Well, that conversation still is important here and applies in this situation. So every time you have an X-intercept, whether you're dealing with a polynomial or a rational function, you're going to consider the multiplicity of that X-intercept. That's why I write them. All right, what else did we do in our algebra courses? Well, like I said, we found Y-intercepts in algebra, but there's a little caveat with generally polynomial, high-degree polynomial, and high-degree rational functions. That caveat is that often it can be very challenging to find, not very challenging, but the numbers can be terrible. I still actually do try to look for Y-intercepts, but only to find out whether they're positive or negative. For example, in this situation right here, if you allow x to be 0, the numerator becomes -3², which is 9, times a -2, which is a -18. I'm not really concerned with the fact that it's actually -18. I'm more concerned with something else here. In the denominator, if you let x equal 0, you have a -4 times a 2, which would be a -8, times 4, which would be -32. The most important part about this is not the numbers, but that it's positive. It's a positive small number, to be honest with you. So I suppose you could, if you wanted to, you could actually reduce that fraction, divide top and bottom by 2, and you get 9/16. And it's positive. I guess I don't need to write the positive now. But the most important part is just know, is the Y-intercept positive or negative? That is very, very, very helpful when you are graphing. If it's easy to compute, then your professor would likely tell you, please compute the y-intercept exactly. But often these end up being super large numbers, and that gets out of control when you try to find the y-intercepts, especially with polynomials. All right, what else did we learn in algebra? So we've already talked about factoring. We talked about the x-intercepts and the y-intercepts. Well, at that point, you're kind of exhausted with all the stuff you learned from algebra. Now you're going to talk about what are the vertical asymptotes. So the vertical asymptotes, let me go ahead and write VA here for vertical asymptotes. Those occur where you have division by 0. And you can see we have some division by 0 going on here. And also where you don't have common factors. So what I mean by that, if you canceled something out, so we had an x plus 4 in the numerator and an x plus 4 in the denominator, those wouldn't contribute to being vertical asymptotes. Unless, by the way, you still had a power in the denominator of an x plus 4, but we don't. So anyhow, those won't contribute to being vertical asymptotes. So we only have to worry about the vertical asymptote at x equals 4. It's odd multiplicity. And x equals -2, which is also odd multiplicity. We're almost done. Now some people might be asking, wait, what about that trinomial off the back end, the x squared minus 2x plus 4? Well, if you have already begun with a sum or difference of cubes, because that's where that factor came from, and if that sum or difference of cubes was already prior to you factoring it, if both of those terms didn't have something in common. So this term and that term don't have anything in common. So once I perform a sum of cubes factorization, I can guarantee that the trinomial on the back end there, that is prime. And what I mean by prime is that it does not factor over the real numbers. It will factor over the complex numbers, but not the real numbers. If you want to prove a really fast kind of aside as to why, I just thought about this and I was like, you know what, it might be nice for those who are really interested in theory. If you're moving on into pre-calculus, you have to get used to proofs. And if you're moving on to calculus, you definitely have to get used to proofs. So let's go ahead and discuss, why is it that that is prime? Well, let's suppose that you were given x cubed plus b cubed, which is what we were given. We were given x cubed plus 2 cubed. Okay. And let's go ahead and just write down the factorization there. That's x plus b times x squared minus bx plus b squared. Well, going to, and I'm going to fix that b right there. Going to the, setting each of these to 0, just to see what would turn them into 0. If you set the first factor into 0, obviously that implies that negative b is a 0 of that polynomial. And then if you set the second factor, the trinomial, to 0, let me go ahead and finish writing that out. You can see that you're going to have to use the quadratic formula here, just because you don't know what b is, so you don't know how that factors. But when you use a quadratic formula, you get, that x will equal a opposite of that b, negative b term, so it'll be b, plus or minus the square root of, again, that middle term squared, so b squared, minus 4 times the leading coefficient times the constant, all over twice the leading coefficient. And if you take a look at this, that would be b plus or minus the square root of a negative 3b squared over 2. That negative 3 is going to lead to an imaginary number. So no matter what, that trinomial will always factor into imaginary factors. The zeros, basically, of this equation, or the roots of that equation right there, are imaginary roots. And therefore, that's kind of a good, strong justification as to why this highlighted trinomial here doesn't lead to any real vertical asymptotes. It only leads to imaginary vertical asymptotes. So that's kind of cool. By the way, if you need to, you're watching this on YouTube, you can always hit pause and try to figure out why that's true. Try to justify. Also, leave comments in the comments section. People are so shy to do that. It's totally okay to say, I don't quite understand, blah, right? And then the community can help. YouTube's not always a terrible place. So maybe we could build a community of people that help each other out. Now, the final move here is to ask, what is the horizontal asymptote, if it has one? And to remind you, all you really need to consider are the degrees of the numerator and the denominator. So let's go ahead. I'm going to write down here the horizontal asymptote, and I'll just mention that the degree of the numerator, I use capital N to talk about the numerator. Well, I'm going to go to you could either go to the original polynomial, rational function, or you can go to your factored rational function. It actually does not matter. But the degree of the numerator, let's just focus on the factored rational function here. The degree of the numerator is going to be x squared plus another power of x, so x cubed. So that would be the degree of the numerator would be a 3. Let me go ahead and just make that mention here. And the degree of the denominator, again, going to our factored version, you'll have a power of x from this guy, a power of x from that guy, and 2 powers of x from that trinomial there. So you have a 4th degree polynomial in that denominator. So the degree of the denominator is 4. Notice the denominator has larger degree than the numerator. Thus, as time goes on, and I really do mean as x goes to infinity or as x goes to negative infinity, our rational function, again, I should write this out with calculus notation. So I'll say as x tends to go to plus or minus infinity, the rational function will tend to mimic roughly 1 over x. Now you may say, wait a second, I totally don't get why you said 1 over x. It's actually not 1 over x, but we'll just take a look. If you look at the numerator way up here, if you had multiplied out everything, it would actually be a 3x cubed. You'd have the 3 from here, you'd have a power of x from there, and you have 2 powers of x from here after you square it out. So you'd have a 3x cubed. I'll just go ahead and write that, 3x cubed. The denominator, on the other hand, if you had multiplied it out, you'd get a power of x here, a power of x there, and 2 powers of x on the back end there. So you'd have x to the 4th, and the coefficient would be 1 because there's no non-unit coefficients on those. So you have x to the 4th, and this would simplify down to be 3 over x. As x goes to positive or negative infinity, so x is getting massive. Think of in the trillions, the quadrillions, the quintillions. These are massive, massive numbers, and you have 3 over that. Now, if I told you you have 3/10 of a dollar, you would have 30 cents. If I said you have 3/100ths of a dollar, you'd have 3 pennies. If I said you had 3/1000ths of a dollar, you would have less than a penny. Notice you're getting less and less money as time goes on. So if I said you have 3/quintillionths of a dollar, you really have pretty much nothing. And so that, as x goes to infinity, tends to 0. So we happen to know that the horizontal asymptote is y equals 0. Good conversation. The more you see this, the easier that conversation is to have. Now I'm just going to go ahead and scroll down and graph out a set of axes, and we'll start our actual full graph. Now, to start the full graph, I just have to be very, very aware of the scale of our x values. So every x value you see, we have x intercepts at 3, at 2/3, we have vertical asymptotes at 4, at -2. So I know that I need to include x values at least going to 4. So I think what I'm gonna do is maybe go all the way to like maybe 6 or 10 or something like that. Let me mark them out. So notice how I did that. I just made it kind of equal distant hash marks, and I decided to make them each hash mark a distance of 2. Now let's take a look at the y values. The y values are kind of they're still important, but we don't have a lot listed here. We have a y value at 0, -9/16, so I need at least, let's say, 1 as a y value. And then we have a vertical asymptote at 0, y equals 0. So the y scale does not need to be as crazy as the x scale, but I'm still going to maybe mark it out in distance of 2. Let's just pretend. So I'll just call that 2, and we'll call this -2. And I don't need to mark off too much there. All right, now we're ready to go. The very first thing I do is just look through the order with which we wrote everything. So for example, my x-intercepts, I have one at 3 and at 2/3. So I'm going to mark those two, and I'll use a different ink for that. So maybe I'll use blue. So here's an x-intercept at 3. Let's just call that 3, 0. And then an x-intercept at 2/3, which might be right around there. So 2/3, 0. Next thing we found was the y-intercept, and as I recall, that was just 9/16. So I'm going to plot a point at roughly a half, so probably right about there. That's 0, 9/16. So far so good. Now I'm going to go ahead and graph my vertical asymptotes, because that's the next thing that we found. X equals 4 and x equals -2 will be vertical asymptotes. Normally, I would draw in like hashed out. I would dash along here, but you know what? I'm just too lazy today. I'm just going to do it this way. Now it's terrible, right? And above them, I will just mark, oh, that's x equals 4. And here's -2. X equals -2. There we go. Another thing I need to always keep in mind is the thing that most of us will forget, which is that x cannot be -4. We have a domain issue at -4. So even though I cannot graph that right now, because I just thought about it, I'm just going to put this x cannot equal -4 kind of above where -4 occurs, just so that I remind myself when I draw this function, there will be a hole in the graph at x equals -4. And then finally, so we've looked through, we've checked this, checked that. We haven't talked about the multiplicities of those yet. We've plotted that and this and this. We haven't, again, stated the multiplicities of the vertical asymptotes, which I could totally do that here. I'll just say odd and odd. That way it's there. And now we have to draw in the horizontal asymptote at y equals 0. And I usually use green for a horizontal asymptote. Notice that it's on the x-axis, so it's really hard to see my green, but that's okay. I just know it's there. That's all that matters. And then you start graphing. We go with my blue pen to start graphing. Now, if your graph, and this is a big if, but if your graph has a y-intercept, that's where you start graphing. That's my professional opinion. So let's start at this y-intercept. It's a function, so it's not going to do something like this, because it wouldn't pass the vertical line test. Now, when I started the y-intercept, you could start graphing to the right, or you could start graphing to the left. I generally like to start graphing to the left for some weird reason. That's just a habit of mine. It doesn't really matter, but I'm just telling you that's how I'm going to do it. When you graph to the left here, you have two options. Either it's going to go up or it's going to go down. And here is a critical warning for you. You cannot create X intercepts. In fact, that's so important that I'm going to write it off to the side here. Don't create non-existent intercepts. Notice that if you had this function go down, it would all of a sudden create an intercept that we initially did not have. So it can't go that direction. Because that, I know that when I start graphing this function, it will actually go to the left and up, and it will never touch a vertical asymptote. So it's just going to kind of bow up, but it will never actually ever touch this vertical asymptote. It'll get infinitesimally close to it, but it will never touch it. Once I do that, I could actually go back to the y-intercept and graph going to the right, but I'm not going to yet, actually. Now that I show that it's going, the function, when I say it, I mean the function. Now that I see that it is going up as x approaches -2 from the right-hand side of that vertical asymptote, and because I know that vertical asymptote has odd multiplicity, well, I know it's happening on the other side. It's the opposite behavior because it's odd multiplicity. So if it was going up on one side, it starts by going down on the other side. And then I'm just going to graph to the left here. There are no other x intercepts on this side of our vertical asymptote, but you'll want to graph to the left. So you want this to slowly curve to the left. And the deal is that we know we have a horizontal asymptote at y equals 0. That is, as time goes on, our function here will want to approach the height of 0. It won't actually touch a height of 0, but it'll get infinitesimally close to that height of 0. All right, now we go back to that vertical intercept. We're done graphing to the left of the y-axis. Let's graph to the right. Well, again, I'm at this vertical intercept. It could go up or it could go down. Well, I got to tell you, you don't know actually exactly which way it goes, but the reality is it will want to be drawn like a magnet to this x-intercept. And once you start talking about x-intercepts, you really need to pay attention to their multiplicities. So let me zoom out and note the multiplicity on the x-intercept of 2/3 is 1. The multiplicity on the x-intercept at 3 is 2. So at x equals 2/3, it's going to look like a line going through. So I know it's going to look something like this. It could have, I'm not trying to tell you it doesn't go up. It might go up, but then it'll eventually come right back down and go right through that. So I just prefer to write it as if it's just going down and going through. Now, as you continue graphing to the left, it'll want to be drawn back to the x-axis to run into the next x-intercept. But remember, the multiplicity of this x-intercept is multiplicity 2. This one was multiplicity 1. And so as your function tends back to that x-intercept, it'll look like a parabola, albeit upside down because of where you're approaching it from. It still looks like a parabola. And because there's no way for it to go back up, because you would create an intercept, it's going to now forever go down. Now let's take a look at the multiplicity of that vertical asymptote. That vertical asymptote has odd multiplicity. Therefore, if it's going down on one side, it's going up on the other, it being the function. Note there are no other x-intercepts, so when I keep drawing to the right here, it's not going to fall and hit the x-axis, but because we have a horizontal asymptote at a height of 0, it's going to want to approach that height of 0. It'll never actually touch the height of 0, so we'll never touch the x-axis, but it will approach that height. I do want to say here that it'll never touch the x-axis because there's no x-intercepts, no more. But you can, your function, most rational functions, okay, can cross their horizontal asymptotes most of the time. They can do that. It's just in this case, for it to cross the horizontal asymptote, it'd have to have x-intercept, and it just doesn't. Now, I said that we're actually done with this, but there's one thing that's super dangerous that we completely did not mention, even though we wrote it. So people might have already noticed it. But we have mentioned x cannot be a -4. Such a common thing to skip that because it's just not part of the complex graph that you've done here. We completely and totally just missed that. So let's go ahead and go back and fix that. How do you fix that? Just erase that little area right there because this is x equals -4 right here. And we're going to put a little hole in our graph right here. It's actually a pretty sizable hole in the graph, to be honest with you. by my visual. But there you go. Now that graph is completely done. I apologize. I did not pay attention to that until right before I switched this page, and I was like, wait a second, we still have a domain issue. Super easy to forget that. And it's so common that, like I said, I almost did it. I almost walked away from this example, and then I realized, whoops, we have a domain issue. These are, you can kind of avoid that by constantly making little notes, like pointing arrows and saying, like, don't forget you have this domain issue at -4. Now the graph is completely done. So here's the next example, and it's almost identical to the last example, except we have a little extra x that's right in front of our function. So what we get to do is copy a lot of our previous work and add a couple little details. And that is literally what I just did. So I'm going to go ahead and erase the pieces that we don't need right now. So I'll just go ahead and erase all this. And I'll add in the pieces that are different. So we have an X here instead of not having one. Otherwise, we'll just make some minor changes. Let's go through step by step and see what happens. So we have factored this, the numerator and denominator. And it's the same factor, so no big deal. Except I have this X sitting out front right here. Great. And then we say, all right, now we need to know, remember, we had the X plus 4's cancel, so we still have that X can't be a -4, which hopefully this time I don't forget. And remember that trinomial is prime. All this stuff I just talked about. Now the X intercepts occur when the numerator becomes 0. So we still have 2 of the same X intercepts, but we have a third X intercept at 0 because of this guy right here. That factor becomes 0 when X is 0. And that's multiplicity 1. The Y-intercept will actually change here because if you try to let X equal 0, not that if you try, but if you let X equal 0, that whole numerator actually becomes 0. Test it out. Let X equal 0 here. You'd have 0 times who cares over something non-zero. So it's 0. So that's now our new Y-intercept. Let's see, going through. So we did X-intercepts, Y-intercepts, going through algebra. Factored X-intercepts, Y-intercepts. Now we're going to worry about vertical asymptotes. Those occur when you have division by 0 after you have completely factored. And there we have same vertical asymptotes. So everything is almost the same. And then finally, you deal with horizontal asymptotes. Let's see, what's the degree of this numerator now? Well, we have a power of X here. We have 2 powers of X there and a power of X there. So it's 4 powers on X when everything's distributed out. And that means that this is like a 3x to the 4th or a 4th degree polynomial in the numerator. So let me go down here. The degree of the numerator is 4. The degree of the denominator hasn't changed because we did nothing to the denominator. So the degrees of both the numerator and the denominator match. If that is the case, then the long run behavior as X goes to infinity is not going to be 0. But you don't have to memorize this. You could just say, well, as X goes to plus or minus infinity, our function is going to approach not a 3x cubed, but actually, if you go back to the polynomial and tried to multiply things out visually, you would see it's a 3x to the 4th. Again, just go back to this polynomial here. Had you multiplied out that numerator, you'd get a power of X, 2 powers of X, and then another power of X with a 3 on it. So you'd have a 3x to the 4th. That's why I write, oh, this is like 3x to the 4th over x to the 4th, which is 3. So in the long run, as X goes to positive or negative infinity, the Y values, which are the function values, approach 3. So our horizontal asymptote is Y equals 3. All the Y values want to tend to a height of 3 as X gets huge. All right, now we're ready to graph. So again, all that setup, once you learn kind of how quickly things go, it really does happen very quickly to be able to graph these. This is my x-axis, here's my y-axis, and I'll plot my x-intercepts, which are at 3, 2/3, and 0. I'm going to have the same scale here if you don't mind, so 2, 4, 6, 8, and 10, negative 2, negative 4, negative 6, negative 8, negative 10, and 2, 4, 6, and negative 2, 4, and 6. All right. So let's plot those x-intercepts. 3, 2/3, and 0. I'll use blue ink again. So 3, 2/3, which might be around here, and 0. I'm not going to label that just because everybody knows what that point is anyway, and I'll end up running ink into each other if I do that. So you might want to state the multiplicities, because I have already made that mistake of not remembering, like, for example, x equals negative 4. Can't happen, so I just put that in there. So if you need the reminder, it might be nice to write their multiplicities in there. I know x equals 3 is a x-intercept of multiplicity 2. The other two, I'm not going to write multiplicity 1. I'll assume it's multiplicity 1 if I didn't write anything there. All right, now let's draw in the vertical asymptotes, which occur at 4 and negative 2. Again, I'm going to do what I did last time. Normally, I would dash out a line, but it's honestly just as nice just to draw an actual solid line. So I'll just call this x equals 4. And here's x equals negative 2. Again, they're odd. Both those are odd multiplicity. Nothing's happened. Nothing's changed there. And finally, my horizontal asymptote, and that's y equals 3. So I'm going to draw a horizontal line at y equals 3. Again, I would normally dash this out, but I'm just being lazy, and there's nothing wrong with you doing a solid line there. These are my guides to graphing. Now, here's the deal. If your y-intercept is at the origin, it is actually not so obvious which direction your curve is going at that after it to the left. It's not so obvious if your curve is going to go up or down. You just don't know. So how do you figure that out? Well, if it's impossible for you to know whether it's going up or down as you draw to the left, plug in a value between this x equals 0 and this x equals negative 2. I'm choosing negative 1. Plug that into your original function. So let me go to my original function. You don't actually have to go to the original. You can go to the factored version. And so I could say, well, g of, I'll write this down here, negative 1. Now, you don't actually need to find out the value. What you need to do is find if it's positive or negative. So let's see, you plug that in, you'll get a negative 1 times some number squared, which will be positive, times negative 3 minus 2, which is a negative number. Notice I don't care about the numbers themselves. I just care about whether they're positive or negative. In the denominator, if you plug in negative 1, you'll have negative 1 minus 4, which is negative. You'll have negative 1 plus 2, which is positive. And you'll have negative 1 squared, positive, minus 2 times negative 1, positive, plus 4, which is still positive. All right. So this is going to be, in the numerator, a product of a couple negatives is positive, times a positive, it's positive. In the denominator, a couple positives, well, that makes a positive, times a negative makes a negative. So you know that this is some negative number. So what does that mean? It means that when you plug in negative 1 into your function g, the value will be below the x-axis. So it's going to fall here. It's not going to come back up, by the way. It's not going to all of a sudden do this because there's no x-intercept. So it's just going to fall as you graph to the left. And this is totally bothering me with that vertical asymptote being slightly bowed. So there we go. And now that I've figured that out, I'll go ahead and use the fact that that vertical asymptote has odd multiplicity to state, well, if it's falling on the right-hand side of that vertical asymptote, it must be rising on the other side because it's odd multiplicity. All right. And remember, there are no other x-intercepts to the left of this vertical asymptote, so it's not going to just fall down here and cross. There's no more x-intercepts. Plus, there's a horizontal asymptote. It'll want to approach that horizontal asymptote as you draw to the left. Now, this time, I'm not going to forget that there is, this is terrible. Let's zoom in a little bit. I'm not going to forget that I have a hole in the graph at x equals -4. I just have to keep that visual there. So I'm going to get right about to there. And I'll put a big old open hole. Notice I'm not plotting points. I'm not like, the only point that I actually plotted was, or I didn't even plot. The only point that I went to evaluate was g at -1, just to see if it's positive or negative. I didn't actually find its value though. So notice I'm not point plotting to graph this. You should never do that. Another thing I want to mention, I stated it last time, is that it could be the case that this function might dip below and do this. It could be the case it does that. It could also be the case, oops, didn't want to do that. It could also be the case that it dips below, goes up, dips below, goes up, and does this. Totally could do that. But I'm going to pretend as though it does neither of those. It doesn't hurt to cross, but I'm just assuming that's not going to. In calculus, you can find out exactly when it crosses. Actually, you don't need calculus for that. You just need algebra. But I don't require my students to find out if it crosses or not. So, all right, so we can see what this rational function looks like to the left of the y-axis. Now let's go ahead and see what it looks like to the right of the y-axis. Remember, our x-intercepts, I've already labeled their multiplicities. If I didn't label the multiplicity, it is 1. That is, the x-intercept at 0 here is a intercept of multiplicity 1, so it looks like a line going through it. It'll want to gravitate immediately back like a magnet to the next x-intercept, which is also multiplicity 1, so it's going to go through that intercept like a line. And then it'll avoid hitting all these numbers. It's going to want to curl back to the next x-intercept like a magnet, but this one is multiplicity 2, so it's going to look like a parabola bouncing right off of it. Now, the conversations that we had in the section based on polynomial graphs still hold. And what I mean by that is, what if, let me finish drawing at least this. What if the multiplicity was not 2, but what if it was 6? Well, then it would be much flatter here. Okay, so that's what a higher multiplicity will do, is it'll make it flatter for a longer period of time. So you do have to keep that in mind. If you haven't watched my video on multiplicities of zeros of polynomials, you should do that. Now, a lot of students I see will stop here because they just think, oh, there are only 2 parts to every rational graph. That's not true. We still have to graph on the other side of this vertical asymptote. Luckily, we know that vertical asymptote has odd multiplicity. Since it's going down on one side, it'll be starting high on the other side. And then as you draw to the right, it'll want to approach the horizontal asymptote. There are no holes in the graph, so I can just smoothly try to graph this out. It'll want to approach that height of 3. Again, that level of detail is what I expect from all of my college algebra students. And yeah, that's pretty much it. It's really a decent graph. So we've dealt with 2 rational functions, one with a horizontal asymptote at 0 and one with a horizontal asymptote at 3. The only other case that we haven't considered is what if it doesn't have a horizontal asymptote? And that's why I have this more simple function, rational function here, because it kind of demonstrates that idea. So somebody says graph this. Let's just go from beginning to end. So what did I first learn in algebra? Oh, I learned how to factor. So let me go ahead and factor. Notice that 18 and 81 both have a 9 in common. So I'll factor out a 9. I'll be left with a 9x squared. Whoops. 9x squared and a minus 2. In the denominator, there's not much I can do. 3x minus 2. Now, that's it's pretty much factored. Actually, technically, you could factor that numerator a little further. A lot of people don't see that they can, but that is actually a difference of squares. But it's not the difference of perfect squares. But I'm not going to bother factoring it. I don't feel that it's necessary to factor that expression in the numerator. So I'll leave it like that for now. All right, so we're done factoring, quote unquote. And now let's talk about the X intercepts. Those occur when the numerator is 0. So we're going to solve it. Well, they occur when y is 0, but that means that they occur when the fraction there is 0, which means the numerator is 0. So we're going to solve 9x squared minus 2 is equal to 0. And that will imply x squared is equal to 2/9, or in other words, that x itself is equal to plus or minus root 2 over 3. So that numerator actually does have zeros. They're just not rational zeros. They're irrational zeros, but that's okay. Let's see, what else? We found x-intercepts. Let's go ahead and worry about y-intercepts, right? And by the way, I pluralized that, but you never would have 2 y-intercepts if it's a function. So we're going to find the y-intercept. This is kind of a good function to deal with because y-intercepts are much easier to find if you didn't factor. Because all you're doing is allowing x to be 0. And so that's negative 18 over negative 2, or in other words, 9. So when x is 0, y is 9. I'm fast, right? Let's see, algebra, what did we learn? We learned factoring, we learned how to find x-intercepts and y-intercepts. And now I kind of graduate into college algebra and I say, I need vertical asymptotes. So vertical asymptote is where you have division by 0. Notice we have division by 0 when that 3x minus 2 is 0. Or in other words, when x is equal to 2/3. This is kind of a dangerous example visually because some people will say, oh, that numerator factors to 3x minus 2, 3x plus 2. I will see people do that. That's not what that factors into. Please don't do that. All right. Let's see. And now horizontal asymptote. Now, here's the deal. The degree of the numerator, just look at the original function. It's much easier. The degree of the numerator is 2. And that's greater than the degree of the denominator, which is 1. If that is the case, then as time goes on, the numerator takes over and you will have an x in that numerator and it'll become ultimately very powerful. And this will not tend to a finite number, but it will tend to a pattern. So because the degree of the numerator is greater than the degree of the denominator, we actually do not have a horizontal asymptote, but we do have what most, if not all, textbooks call a slant asymptote, which is a terrible name. It's a terrible name because it's only used if your asymptote is a line, but your asymptote might not be a line. It might be a parabola, a cubic, a quartic, or something like that. Or it could be an exponential, actually, once you reach calculus. So slant asymptote's a terrible name. It should be called oblique. But unfortunately, that's just the choice of the math community, right? So how do you find the equation of the slant asymptote? Well, we talked about that in the previous videos in this series, specifically the identifying slant asymptotes of rational functions. We talked about it there. So let's go ahead and use that technique. We're just going to take the divisor, 3x minus 2, and divide it into the dividend, which is 81x squared plus 0x minus 18. And the quotient of this will be our slant asymptote. So let's see, how many times does 3x go into this 81x squared? Well, 81x squared divided by 3x, that'll be 27x times. So I'm going to put that in the x column, 27x. What's beautiful about long division is you get to check your work. 27x times 3x, that's definitely 81x x squared. 27x times a negative 2, that's a negative 54, x. And remember, you are subtracting that entire statement. 81x squared minus 81x squared is 0 by design. If it doesn't turn into 0, you did something wrong. 0x minus a negative 54x is a positive 54x minus 18. And then you ask, how many times does 3x go into 54x? And that would be 18 times. So I'm going to write, in fact, I should probably write it over here. I'm asking how many times does that 3x go into 54x? And the x's will cancel. 3 goes into 54 18 times. So there we go. So I know it's a positive 18 times. You could double check your work by distributing back through, but I'm telling you it is true. 54x, 18 times a negative 2 is a negative 36. There's no reason for me to go any further because I've found the quotient, but I just want to showcase that I can't go any further. So I'm just going to show you as a student. Negative 18 plus 36 is going to be a positive 18. That's the remainder. And the remainder is not in consideration when you're doing this process. So I'm done. Why do I know it's the remainder? Well, because when you ask how many times does 3x go into 18, you're going to have an answer of it doesn't. Okay. 18 divided by 3x is 6 over x. So that x doesn't go in. And that's not what we want. We want to have a polynomial answer, not a rational answer like that. So I will X that out. And now I see my slant asymptote is this quotient right there. So slant asymptote is y equals 27x plus 18. A ridiculous slant asymptote. For anybody who's done this work before, you will notice that is a stupid slant asymptote. And because of that, you have to be very, very, very careful when graphing this. And this is true, by the way, this is always the case when you're dealing with slant or oblique asymptotes, is that things can get out of control very, very quickly. So I would recommend, if you're working with a slant asymptote like this, or an oblique asymptote, to graph that first. Graph it to where you can see it cleanly on your paper. Notice this is a line with a y-intercept of 18 and a slope of 27. So the rise over run is 27. That's ridiculous. So essentially I need to scale my y-axis in such a way that 18 doesn't occur way up here, because I need to also show it rising 27 units and running 1. So it's a ridiculous scale. But let's see how we could do this. So I'm going to pretend as though maybe this is a height of 20. I'm just, look how stupid that the scale on the y-axis is. And if that's the case, then this would obviously be 40, this would be 60, and this would be 80. I'll just put here, this is negative 20. This would be 40, 60, and 80. And let's see what else we have as far as numbers before I graph. So my X intercepts are super close to the x-axis. They're plus or minus root 2 over 3. Those are small numbers. My y-intercept, though, is just at 0.9. That will be pretty okay. And then my f of vertical asymptote at 2/3. So my x value scale is really small. Okay, so that's going to be a bit of an annoyance. So I'm going to do this. I'm going to say this is 1, 2, and 3. I'm just going to go out that far for now. And now I'll go ahead and just sort of graph my slant asymptote. Notice the scale I chose for my x-axis is really different than the scale I chose for my y-axis, and that's just so that it can be helpful. So my slant asymptote, I kind of always do those in green. It has a y-intercept of 18, and then it rises 27 units for every 1 it runs. So here's 20 units up, so maybe 27 units would be right here, and it runs 1. So possibly right like this. So that was a run of 1, and it rose all the way up 20 units plus an extra 7. So I'm just eyeballing it and saying that's about 27 units up. And then because it's a line, I'm going to connect those two dots with a line, and I label appropriately. Notice now that the scale is built such that I can actually see this line in my square grid there. Now I worry about everything else. Okay, what are my x-intercepts? They're at plus or minus root 2 over 3. Okay, so that's going to be quite a bit of eyeballing. You might need a calculator because root 2 is 1.414. It might be nicer to just grab a calculator to figure out roughly what those are. And they're roughly a half. I just grabbed a calculator, so it's roughly around a half. So I have x-intercepts at around a half. So I'll go ahead and use blue for my graph here. Here's my first x-intercept at, again, it's a square root of 2 over 3, comma 0. And my second intercept is, and if my scale holds here, I'm going to use this. This might be a negative one. So my second x-intercept is at roughly a negative half, maybe actually right there. And I'll just write negative root 2 over 3, comma 0. My y-intercept is at 0, comma 9. Also, by the way, I should note, the multiplicities of those x-intercepts, they're just 1. So I'm not going to bother worrying about labeling those. Those are x-intercepts with multiplicities 1. And now my y-intercept is 0, comma 9. So that's going to be somewhere around maybe here. Again, this time I'm going to point an arrow just so I can see it. 0, comma 9. And now let's deal with the vertical asymptotes. Oh, we only have one, and it's at x equals 2/3. Oh, it's going to be a mess in here, but now 2/3 is 0.666 on forever, and that's beyond this 0.5. So I'm going to put this right about here. This will be my vertical asymptote. I can zoom out and actually finish it out here. X equals 2/3, and remember that's an odd multiplicity. That was the power on that. And at this point, I'm ready to graph. There's nothing else I can, draw out here. So I'm going to go ahead and graph this function. Again, I start at the y-intercept if I can. If you don't have a y-intercept, then you're going to have to start by plotting a point elsewhere. That's the only way. Either you start at a y-intercept and then move left or right, and use the graph to kind of help you decide which direction to go. Or if you don't have a y-intercept because you're dividing by x at some point, you then have to at least try 1 point. But in this case, we're lucky. We know as we draw it to the left, it'll want to tend to this x-intercept and go through it like a line. That's pretty good. If I keep drawing to the left, it'll want to hug this slant asymptote. That's the whole idea of having a slant asymptote. So it's going to want to hug this slant asymptote all the way down forever. It's like a little magnet. It keeps it really close to the slant asymptote. Now that I'm done drawing to the left of the y-axis, I will draw to the right of the y-axis. I have two choices. It could go up or it could go down. Well, obviously there's an x-intercept, so I'm going to have it draw down. It'll cross through like a line because the multiplicity of that x-intercept is 1. And then it'll just bow down forever, trying to get infinitesimally close to that vertical asymptote. The vertical asymptote has odd multiplicity, so it's going down on one side. That means it starts high on the other side. There are no more x-intercepts, so I don't have to worry about this thing diving down and crossing. But it will, as you draw to the right, want to bow to match this slant asymptote. Remember, it can actually cross an oblique or slant asymptote. It can also cross horizontal asymptotes, but I don't really require my students to say that it does or doesn't. I just want the full pattern. And that is actually a beautiful graph of that function. My warning here about drawing your slant or oblique asymptote first is super important, because your scale is going to just go out of whack if you draw it last. So I highly recommend drawing your oblique or vertical asymptote, oblique or slant asymptotes first, and scale it in such a way that you can actually see that asymptote for the entire grid. So notice I did ridiculous scaling here, but in the end, it ends up looking like a pretty decent graph. If you did this freehand and graphed that slant asymptote last, it would look terrible, trust me. All right, that's it for graphing rational functions for college algebra.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.